Hello everyone, I am an avatar created by Yili Lin, a doctoral student in health services research at the Department of Health Administration and Policy, George Mason University. Let's continue our discussion on model selection. To determine which model provides the best balance between fit and complexity, use model selection techniques. Cross-validation is a powerful technique used to assess the validity of a model and to support model selection. By applying cross-validation to different models or configurations, you can compute performance metrics for each model. The model with the best average performance across the cross-validation folds is often chosen as the final model. This approach helps mitigate overfitting and ensures that the selected model is robust. When comparing multiple models, you calculate the Akaike Information Criterion, AIC, and Bayesian Information Criterion, BIC, for each model. The model with the lowest AIC or BIC is typically preferred. Both provide a balance between goodness of fit and model complexity, helping to avoid overfitting. While AIC is more focused on minimizing information loss, BIC incorporates the sample size more heavily in penalizing complexity. When dealing with many predictors, regularization techniques like ridge and lasso penalize large coefficients, controlling overfitting. Stepwise regression automatically selects a subset of variables based on AIC or BIC or p-values. The methods you can use include forward selection. Start with no predictors and add the most significant one step by step. Backward selection. Start with all predictors and remove the least significant one step by step. Or combine forward and backward approaches. After fitting your model, you need to evaluate how well it predicts or explains the dependent variable. R-squared represents the proportion of variance explained by the model. However, it increases with the number of predictors, so be cautious of overfitting. Adjusted R-squared adjusts for the number of predictors, providing a better comparison between models with different numbers of predictors. Root mean squared error measures the average magnitude of prediction errors. Residual plots visualize residuals to ensure there's no clear pattern. Residuals should be randomly scattered around 0, indicating a good fit. Overfitting occurs when a model becomes too complex by including too many variables or parameters, causing it to fit the training data extremely well, including capturing noise and random fluctuations. As a result, the model performs poorly on new, unseen data because it has learned patterns specific to the training data rather than generalizing to the true underlying trends. Therefore, you can compare training and testing error. A large difference suggests overfitting. Cross-validation scores regularly perform cross-validation to ensure the model generalizes well to unseen data. Simplify the model. If the model is too complex, reduce the number of predictors or regularize using ridge-lasso regression. After evaluating different models, select the one that balances prediction accuracy and simplicity. Use performance metrics like AIC or BIC, cross-validation results, and residual analysis to make your final choice. Finally, interpret the results. Each coefficient represents the expected change in the dependent variable for a one-unit change in the predictor, holding all other variables constant. If two predictors are highly correlated, their individual coefficients may be unreliable, even if the overall model fits well. Use a separate test set or external dataset to validate the model's performance. By following these steps, you ensure a systematic approach to model selection, maximizing accuracy while minimizing overfitting and complexity. The process is inherently iterative. In practice, the steps you follow in model selection and refinement are often revisited multiple times as you learn more about your data and the relationships within it.